0.6. Okay, we're going to work through this problem together. And let's start with the setup. Okay, so the question says, Jamestown Steel manufactures and assembles desks and other office equipment. The mean weekly production of the Model 835 desk follows a normal distribution with a mean of 200 and a standard deviation of 16. This is the population data for this. Recently, new production methods have been introduced and new employees hired. So what we want to know is if there's been a change. So the VP would like to investigate whether there's been a change in the weekly production. We're going to use an alpha of 0.01. And what we find is in the last 50 weeks, the mean number of desks produced was 203.5. The next slide will go through a video tutorial of how to solve this problem. Okay, here we go. Testing for the population mean with a known population standard deviation. So again, we know the population standard deviation in this case. Let's write down all the information that we're given in this problem. First, we're told that mu, the population mean, is equal to 200. So this is their regular operation, or status quo. We're told that the population standard deviation is 16. Okay, so what do we want to know in this question? We want to know is, has there been a change in the weekly production of the desk using an alpha of 0.01? So let's set up our hypothesis test. So here we go, step one. All right, step one is to actually write in our hypothesis. Okay, so H0, our null, and our alternate. So our alternate in this case is basically that the mean has in fact changed, and now that the mean is different from 200. Okay, and that means our null is the status quo, which means that the mean is equal to 200. Okay, so that's our starting point. So notice, what did I use? Well, I used a piece of the information from the question saying that the initial mean was 200, and looked at what we're trying to do and what we're trying to test, and we're just testing to see if there's been any kind of adjustment since the new staff was hired and the new production methods were introduced. Okay, now we need to ask the question is, how many tail test is this? So is this a one tail test or two tail test? Notice that our hypothesis, right, our null and alternate hypothesis, do not state a direction of change. All we want to know is, has there been a change? And since that's the case, since we don't know whether it's a decrease or increase, we're going to be looking at a two-tail test. Right? And again, the reason is that we don't have a direction. Okay, let's go on to step two. So step two is basically our alpha. And in this case, we'll see in the problem, you'll notice that alpha is set to 0.01, okay? And of course, this is a two-tail test as we discussed. Let's go on to step three. Step three, right? Remember, this is the question of which test statistic to use. So we're basically, it's either a z-test or a t-test. So z-test or t-test. And in this case, we know that sigma is known and given to us in the beginning of the problem, and therefore we will be using a z-test. Okay, step four. Step four sets up our decision rule, right? This is where we basically create the criteria for our test. So our decision rule. So now think back on the process that we just did in a previous video where we estimated the z-critical value for a two-sided test. So let's draw our distribution. Right, this is a two-sided z-test. And here's going to be our z-critical values. So z-critical value, negative, and a z-critical value in the positive side. Now we know that if we get a test statistic that is less than our z-critical value, this is our reject area, greater than the z-critical value, also a reject area, and if we get any value in between the z values, this is fail to reject. Okay, so let's see what we get. What is our z critical value in this case? So let's follow our steps for the two-sided test. So step 1 is we take 0.5 and we subtract alpha divided by 2. So we get 0.01 divided by 2. So this will be 0.5 minus 0.005, so we get 0.495. Step 2, we have to go to our z table and look up 0.495 in the body of the z table. Okay, so when we do that, when we look up 0.495 in the body of the z table, we get a z value of 2.58. Again, if this is unclear, please see the previous video that discusses how to find those critical regions. Okay, so let's label our critical values. So we have negative 2.58 and positive 2.58. So this is step 4, our decision rule. Now let's go on to step 5. This is our z-test. Okay, so our z-test is comprised of a few steps. So what we do here is we have to find the z-value or the z-test statistic found by x bar, the mean of our sample, minus mu, the mean of the population, divided by sigma over square root of n. I believe we have seen this equation before. So what are we told in this problem? We're told here that the x bar is 203.5, that the mean, the mu is 200, and sigma is 16. And we're told that we've been in production for 50 weeks, so n is going to be equal to 50. So let's put in our values here. So z equals x bar, so we have 203.5 minus 200 divided by 16 over the square root of 50, and this gives us a z statistic of 1.55. Now what? Well, now we go back to our rejection regions, our critical values, and we see where this lands. Is it in the reject or fail to reject region? Okay, so let's go back to our step 4 here. Okay, and let's label our 1.55. So this is 2.58 here, right? So this must be 1.55. Okay, and you can tell that 1.55 is very clearly in the fail to reject region. And so in this case, we fail to reject the null hypothesis. Okay, and what does that mean? Let's write that down as like a sentence. And what does that mean? It means that there is not enough evidence, or the sample doesn't provide enough evidence to suggest that the mean is now different than 200. Okay, so we don't have enough evidence to prove that there has actually been any change. So we could say there is no evidence, or actually let's state it this way. Let's say there is not enough evidence to prove that the new production methods and employees have made a difference in weekly production or 2-weekly production. Okay, step 6. Okay, step 6. Step 6 is our p-value. Okay, this is basically the probability that our result is due to chance. Okay, so this is represented by the p-value. Okay, so how do we find the p-value? So based on our example, we start off again by drawing our distribution. Okay, so we have our distribution. The next thing we do is label our test statistic that we found in step 5. So in our case, it was 1.55. Okay, now what we're going to be doing for the p-value is effectively finding the area in the distribution that is past the test statistic. Now, if you recall, this was a two-sided test or a two-tailed test. Therefore, whatever we do on the right side of the distribution, we in fact also have to do on the left side. So we will also have to find the area in the distribution that is to the left of negative 1.55. So really all we do is find one side and multiply to get the p-value on both. So first, to get our p-value, okay, we start off by 1. Look up the z-value of 1.55 in your z-table. Okay, what do we get? We get that the area, we find that the z-value, right, the area in the z-value that is between 0 and 1.55 in this region is equal to 0.4394. Okay, so in order to get the area in this tail, we do 0.5 minus 0.4394, and we get 0.0606. Okay, so that's this side. Now, since it's a two-tailed test, we have to also replicate this on the left side. And so that's another 0.0606. So since we're doing a two-sided test, we do 0.0606 plus 0.0606, and we get 0.1212. So how do we interpret that? Well, what we would do with this p-value is first we would compare the p to alpha, okay? So when p is greater than alpha, this further gives us evidence that we cannot reject the null. Okay, when in cases where p is less than alpha, this is where we can reject the null. Okay, so in this case, what do we prove? We prove that p is 0.1212, alpha is 0.01. Clearly, p is greater than alpha, and therefore, in this case, we fail to reject the null. Or in other words, the probability that this result is due to chance is 12.12%. And that's too high when it comes to production.